attendance. Attendance. Okay, we are starting a class now. I am not evaluating abhi we are starting a class. Okay? Right. So अब एक बार we had talked about until here, and then approximate Q-learning. Okay. What is Q-learning? देखो, I had delayed this part because इसमें जो आने वाला है most of it you know already. Okay, I just have to connect. What is approximate Q-learning and why do we need it?
We can't store all the random states and form tables. That's why we make a generalization.
Right. So you need to do approximate Q-learning because देखो, we were talking about toy problems. There was a grid, right? And there were some 10-15 states. So how many Q states will be there? Those 15 into 4, 10 into 4, whatever. Okay. Now, if your state space is huge, right? In that case, you will have huge number of Q values, right? And it will probably not be able, Abhinav, will you be able to learn an optimal Q value in just one iteration? No, you get just one sample. So you need to do enough samples in all these states. Now think of it this way, you have a huge state space. To be able to learn optimal Q values, you will have to visit each state sufficient number of times. So one is not sufficient, okay, much more than just one. Ideally we know it is infinite, but we don't want to do that. Learning systems mean we should be able to learn quickly. And what is the basic output of learning? You should be able to generalize well. Okay? If we don't generalize, that's not a good learning algorithm. Now generalizing across states. Okay? So you want to learn a Q function or a function that assigns Q to your states, okay, Q values to your states comma action, right? So you want to assign Q, अब एकदम तमीज से सुनो ये वाली चीजें. You want to assign Q values to, so you want to assign Q of S comma A. You want to assign Q values. पहला तरीका क्या था? What was the first one? That model free one. Go everywhere, take an action there, you will get some reward, okay, and start learning from there. So basically, take a lot of samples in the actual space. Now what we are trying to see here is, we want to, so basic Q learning keeps a So basic Q learning keeps a table of all Q values. We have seen वो जो अपनी grid में था. In realistic situations, this won't be feasible. So we want to generalize, learn about some small number of training states from experience. Generalize that experience to new similar situations. This is a fundamental idea in machine learning. And we'll set it over and we'll see it over again and again. So the most important takeaway of any machine learning algorithm is to be able to generalize well. If it does not generalize, you don't care whether you had a training accuracy of 100%. Okay. So for example, let's say we discover through experience that this state is bad. Okay. In naive Q learning, we know nothing about this state. Okay. But is this state also bad? From this experience, should Pacman have learnt that this particular state is also bad? Because लगभग वही तो है. What about this one? This is exactly same as that one except यहाँ पे food pellet नहीं है. Else this is exactly same as this one. But it's a new state. So what will the algorithm do if I were to take sampling? You will have to go and sample for this state as well. It's a new state. Start from scratch. Start learning Q values. Whereas you should have generalized what you learned here, here, and possibly here as well. Okay.
So this is going to be a very small Pacman board, and what you're going to see is you're going to see a bunch of states fly by. Each state is going to have a Q value for each action, and we're going to slowly learn. So here we go.
So total.
Tiny little board, we died. We died.
Total states कितनी है यहाँ पे? मतलब total, yeah, total states. Total places where Pacman and all these can move. 6. Okay, we continue.
Oh, we won. We died. We died. You mostly died. Why? Because you don't know what's going on. You're like, I've never seen this state. Let's go left. And meanwhile, the ghost is like, yum. Every now and then, you accidentally eat the dot. You lose a lot of Pacman this way.
So what was going on in this one? So you are trying to learn Q values for all the states. Okay. Until you learn all the Q values, you don't really know what is good and what is bad. So you spend a lot of time learning what is good and what is bad.
The regret is very high.
So even though the state space was very small, just 6 states.
Now what I'm going to do is I'm going to let it run 2,000 times before we see anything. After 2,000 times, you've seen all these states before, you know exactly which ones are good or bad, and now you can do some amazing gymnastics and dodge the ghost. And you back that was a win. So you win and you win and you win and you win.
What happened in this case now? They fast forwarded it 2000 steps. That means you have collected enough Q values. Now you know what should you do.
Now what I'm going to do is I'm going to let it run 2,000 times before we see. What about this? run into the ghost. Yeah, so that's basically not going to work. What about this?
So what was one takeaway from this demo? See, if Pacman gets eaten here, is it different from the fact if Pacman gets eaten here? So from game's perspective, it does not matter, right? What's important is to learn is it does not matter which square you are in. You should not get eaten by host, okay? But from mathematical tree's perspective, this state is different from that one. So getting eaten in this particular state is actually different from that one. So to have enough confidence, I again need to have a lot of samples of that kind. Okay. So is this generalizing well? Right? Because your learning was that in this state, if I get eaten by ghost, it is bad. We want our system to generalize that even if in this state I get eaten, then it is also bad. It does not matter where do I get eaten. It is bad for me. Okay. So feature based representations now. Solution is to describe a state using a vector of features. Now you are coming to machine learning that you have already done in last sem. So features are functions from state to real numbers, often 0, 1, that capture important properties of the state. So for example, distance to the closest ghost, distance to closest dot, number of ghost, 1 by distance to dot square, is Pacman in a tunnel, etc. So a lot of features given on the problem at hand. You can also describe a Q state with features. Example, action moves closer to the food. So next thing will be, we'll make it clear. So using feature representation, we can write a Q function or a value function for any state using a few weights. So you can write value. So you can write value as a function of, so value is a function of these features now. Similarly, Q is a value of these features now, right? Have you seen this kind of thing before now? Wx plus b, right? This is what it is. So advantage is our experience is summed up in a few powerful numbers. Disadvantage is that states may share features but actually be very different in value. So these things we know from our previous machine learning. So all we are trying to do here is write Q values as a function of features. Okay? Can anybody guess what are we going to do next? So this is the function, this is our Q function. What are the things that are unknown here? So my weights are unknown, features are something that I have chosen, right? So these guys are known. Q-learning with linear functions. So what is this? This is a transition. What is this guy? What were we calling this part? This was a sample, right? This is my current Q value. How do I update? How does this equation look like? We have seen this before. Right? So basically you update Q as a function of earlier Q and this difference, right? This if you write this again, this is what you will get. Now, ये चीज पहले कब देखी? So you are updating W's. Okay? This is same thing that you have seen earlier, right? So intuitive interpretation is just adjust the weights of active features. if something, so all we are trying to say here is keep on updating W's. Okay. So if this is the feature you have decided, and now, so I don't have much to say. एक second. So what happened in this case? You started with W value, W1 value is 4, W2 value is -1. These are your features. After all this update, W becomes 3 and this -1 becomes -3. Okay. How are we going to update W is a question now. This is something you already know. What is this? Linear regression. Okay. So
What's nice about this is you learn so quickly.
So now, earlier we had a grid of 3 cross 2 and we saw that it struggled to learn good Q values for a long time. Given sufficient time, it was able to learn. Okay. Now see the grid.
From even one experience, you can learn the ghosts are bad. So what you're going to see is you're going to see a game of Pac-Man in a reasonable board with ghosts. And what you should realize is the first time you eat a dot, you get a feedback that lets you learn that maybe dots are good. And the first time you hit a ghost, you have an opportunity to learn that ghosts are bad. So instead of that kind of error and error and error, and finally after 2,000 tries, we master a 2x2 board, let's see what happens. So, dots are good, ghosts are bad. Okay. Dots are good, ghosts are bad. You see, tried to run away. And now, pretty good. Here it's not eating the power pellets. If it ate them, it would have a chance to learn that they're good if the feature functions allow that to be represented. In this case, those features aren't present. What's nice about this is you learn so quickly.
So what happened in this case now? You decided features and all system was supposed to do was learn weights, and that is much more efficient compared to the earlier thing where you were going to every state, take a lot of actions in that particular state of all kind, and then you finally realize which particular action is good. Okay. So from here I think you know it already much better than me. So how does linear regression work? Right. Let's talk about just this one. So what is linear regression? How many of you know linear regression? Raise your hands. So then there is no point. Anybody wants me to repeat? Okay. So then we are done with all these things that we were supposed to do. Why do we take least squares in this case? How many of you know logistic regression as well? So what is the cost function in linear regression? What is the cost function in linear regression? So is it a function of this thing?
Yes.
Okay. So this is what it is. What happens in case of logistic regression? What was the cost function? Yes. What happens in case of logistic regression? What was the cost function? cross entropy, which is so it was y, I mean keep everything aside, just give me the expression y log of y hat plus 1 minus y log of 1 minus y hat. Sum it over all examples, right? Take average and put a negative out there. Okay. Why do we use two different cost functions?
Because they are not continuously vectored. They are continuous together, but they are not continuous separately.
Sorry.
They are continuous together.
No. My question is, why do we use this kind of cost function in linear regression and cross entropy in the other logistic?
One is used for classification, one is used for prediction.
Why?
Prediction one is used in classification and for the outliers will be.
So this same old thing you have done it, right? So I am skipping it and we are done with what we were supposed to do. Overfitting. So what happened? How many of you know here overfitting? So then you know this already. So this is overfitting. So I don't really need to do too much here now. We are done. Okay. These are some of the examples you can watch offline. So class is over and I come back to evaluations now. Okay. Okay, you can see these. So we are done. Okay.